The concept of scanning has been around in science fiction for years. Here are two examples, including a handheld scanner that can diagnose a Romulan tapeworm infestation at 20 paces. And here is a starship sickbay, in which intergalactic medics perform everyday miracles, including scans. The irony is that although the sickbay is a load of sci-fi phooey, the scan itself is a genuine computed tomography reconstruction, so demonstrating that the state of the art of scanning is better than science fiction. This talk is about how computed tomography works. CT is a technique for producing detailed images of the X-ray attenuation with an object. In thinking about CT, there are a number of important themes, including what we mean by a CT image, as well as the mathematical techniques used to construct it. CT was invented by a British scientist, Godfrey Hounsfield, who published the technique in 1968. The first commercial CT scanner was developed in 1972, and Hounsfield was awarded the Nobel Prize in 1979. This shows the experimental rig on which the technique was developed, and the first image of a brain section showing that the technique could work. Early scanners for the brain took a series of sections as shown in this slide. In theory, their thickness is infinitesimal, but in practice they are between 1 to 5 millimeters thick. The image on the left is a CT section through the head. The position of the scan is shown on the right-hand image, which in fact is an MRI scan. Importantly, various brain structures are visible in the CT scan, including the ventricles, the internal capsule through which fibers pass to the cortex, and choroid plexuses that regulate cerebrospinal fluid production. The scanning geometry is achieved by having an X-ray source on a rotating gantry. The source can translate along the gantry. A detector follows the X-ray source. There are two variables related to the scan: rotation of the gantry and the progression of the source along the gantry. This is the coordinate system of the scanner. The rotation of the gantry is theta. The traverse of the X-ray head along the gantry is L. The distance from the source along the X-ray beam is S, and the function measured by the detector is G of L and theta. We now have to consider what is being measured. We have a ray with intensity I0 entering the object and emerging with an intensity I. The attenuation of the ray in the object at any point is equal to minus the intensity at that point times the absorption coefficient mu. This is a separable first-order differential equation, and on integration leads to the important result that the log of the ratio of the incident and emerging intensities is equal to the integral of the attenuation across the path of the ray. In other words, the amount of stuff between the source and the emitter. This is called I sub L to indicate that logs have been taken, or G, which is a function of the traverse of the source and detector L and the rotation of the gantry theta. The aim is to get the value of attenuation at every point along the X-ray path, so leading to sampled values in an XY grid across the object. Here is the projection geometry and coordinate system shown on a phantom that is represented by an XY grid. The lower right-hand graph shows the attenuation along the ray as a function of S, and the upper right-hand graph shows the projection profile as a function of L. At any point L, the projection profile is the integral of the attenuation along the ray. You can now see how the projection profile is generated. The blue line shows the X-ray, and it passes along the gantry with increasing L. This process results in a projection profile, which is taken at each rotation step of the gantry. It is the attenuation along the beam as it travels a distance L along the gantry. We can plot the profile intensity as a grayscale for every value of L on the abscissa and every value of theta on the ordinate. This is known as a sinogram. Despite its name, it has nothing to do with China or even the sinuousness of a snake, but was developed to image the sinuses in the skull. The sinogram is also known as the radon transform, after the physicist who described it. It clearly has something to do with the shape of the image, but it's not obvious what this is. We are trying to describe the attenuation as a function of x and y in the plane of the scan through the object. This is computed as samples rather than as a continuous function, and so we should really say that we will compute the attenuation as a function of n and m. Now we have divided the image into a grid on the xy plane, we are trying to compute the value at each sample point. If we have as many rays passing through the object as there are sample points, we can write the equations for the attenuation of each point in terms of the rays. This, however, isn't as easy as it sounds. If we consider a 2x2 image with attenuations A11, A12, A21 and A22, we can write a set of equations for the unknown attenuation vector A. The matrix C describes the imaging geometry and relates the attenuations to the observed intensity vector B. Solution of this equation yields the attenuations. Now consider a 3x3 image. There have to be 9 equations to solve this system, and the diagonal rays B31, B32 and B33 provide these extra equations. Note that we now have to have non-vertical or horizontal rays to generate the equations. The matrix C describing the imaging geometry has become more complex, reflecting the diagonal and partial intersection of the rays with each cell. Nevertheless, the system is soluble. If we now think about a practical image with, say, 120 by 120 cells, we run into problems. This is because the number of equations increased with the square of the linear dimension of the image, and the size of the matrix C increases with its fourth power. Thus the number of equations is 14,400, and the number of terms in the matrix C is in theory 200 million. Very large systems of equations can be solved. This is difficult and prone to errors. For example, very small errors in measurement may lead to inconsistency in the equations, and the solution may be wildly wrong. In practice, these systems of equations are solved iteratively, in which an initial guess of the solution is made, and then its accuracy is increased in stages. Another issue is the computing power available for the method when it was first developed. The first CT scanner was based on a computer with 32K of memory and a 3.1 MHz clock. Solving the system on this computer and reconstructing a CT image meant that efficient numerical methods had to be used. Most methods of reconstruction are based on back projection. In this method, the density of the projection is smeared across the XY plane at the angle at which it was obtained. These animations show the process of back projection of the profile densities onto the XY plane. Once the back projections have been obtained, they are summed to produce a composite back-projected image. This is illustrated by using a small circular object and using the profiles to form a back-projected image. The profile of the object is easily calculated and is shown here. Due to the symmetry of the object, all the profiles will be identical. Here is a single back projection, two back projections, as the number of projection rises, the object starts to take shape. The back-projected reconstruction is called F sub B of X and Y. While the object seems to be in the right shape, it has become blurred. If we take a section through the reconstruction shown by the yellow line, we can see the computed attenuation profile. What has happened is that the attenuation inside the object has been amplified and it has been spread out outside its original confines, so creating a blurred image. The question we have to answer is what is the relationship between the true image fxy and the back projected image f sub b of x and y. We can start by looking at what happens to the image of a single pixel. This is a very important function known as the spatial impulse response. In generating this image, all the X-rays pass through one point. Imagine that all the photons have passed through this point and are spreading evenly. They spread into area A, which has an area of R1 dr d theta. The intensity, IA, is the total photon energy, E, divided by the area, which is equal to the reciprocal of the radius, R1. The same energy passes into area B, which leads to an intensity proportional to the reciprocal of R2. Therefore, the intensity falls off with the reciprocal of the distance from the point in question. This obviously has radial symmetry and leads to a three-dimensional function shown on the right. The importance of this idea is that every point in the image is blurred by this impulse response, known also as the point spread function, or, for our discussion, the blurring function. It can be shown that this function, for a sampled image, is 1 when r is 0 rather than infinity. Signal processing sometimes involves rather difficult discontinuous functions, and should you study it, you will do this in depth. We are now in a position to apply the point spread function to an actual image. What we are doing is the equivalent mathematical operation as back projection. The way we do this is to take a point ij in the original image. We then multiply or scale the entire point spread function by the amplitude value at the point ij. We then shift the point spread function so that where r equals 0 is placed coincident on the point ij in the image that we are constructing on the right. We now sum every point in the shifted point spread function with every point in the image that we're constructing. We now move to the next point in the original image and repeat the process of scaling the point spread function, laying it on the new image at the point ij plus 1, and adding it to the new image. This is shown in the animation. The point spread function is moved regularly to every non-zero point in the original image, as shown on the left, scaled, and then added to the image we are constructing on the right. You can see that this creates a blurred version of the original image. The process that has just been demonstrated is known as convolution. The back-projected image f sub b is said to have been formed by the convolution between the original image fxy and the blurring function bxy. The convolution operator is indicated by the star symbol. This is a very important idea because it shows the precise mathematical relationship between the original image and the back-projected image. This is why I've made such a meal of explaining it. Because we now understand the blurring of the image, the challenge is to find the inverse, deblurring operation that can be applied to the back-projected image. The blurred back-projected image f sub b xy is the sum of the back projections. We want to find the inverse function r of xy that restores the image by convolution with the blurred image. It can be shown that instead of operating on the blurred image as a whole, each projection can be deblurred individually and then back projected to form the unblurred image, and this is the approach to use. One rather nasty thing about CT is that the projections are taken radially and so are naturally expressed in polar coordinates, while we want to reconstruct the image in Cartesian coordinates. We now need to look a bit more closely at convolution in one dimension. This is a very general operation in the analysis of linear systems. We start with an input function x, which in our case is intensity. Note that we're dealing with samples as opposed to a continuous function. The deblurring function is conventionally and rather confusingly called h in one dimension, and in this example I've made it only 3 samples long. The first step is to place the center of h at the sample where you want to start. Then each sample x is multiplied by the corresponding value of h to yield xhi. These values are then summed to yield the output sample, or, as it is known in this context, the filtered sample. The deblurring function h is then shifted by one sample, and the process is repeated to give the second output sample, and then shifted again by one sample to produce the third output. This animation shows the deblurring function, in yellow, being convolved with 3 single-sample impulses in the lower row. The product between the input and h is shown in green, and the sum of the product, i.e. the output, is shown in light blue. The convolution of the deblurring function with an impulse is simply the deblurring function. This shows the convolution with rectangular pulses by exactly the same process. These pulses are equivalent to an area of uniform intensity in the image, and the output shows how the process of back projection modifies them. A circular object with a uniform attenuation has a rectangular section through it. This section corresponds to an unfiltered projection. We can create the actual projection by convolving this section with the blurring function to give a modified blurred section. These sections can then be combined by interpolation to give the blurred image that results from back projection reconstruction. We can now see how to deblur the image. An impulse is convolved with the blurring function to give the blurred function. We want the inverse function that, when convolved with the blurring function, yields an impulse. Note that an impulse is represented mathematically by the delta function occurring at, as shown here, at point L. The deblurring function will tend to be negative where the blurring function is positive, and must be constrained so that its convolution with the blurring function has an output that is 1 at L equals 0 and 0 everywhere else. Thus, we can either use a two-dimensional deblurring process, which is unsatisfactory for a number of reasons, or we can apply a one-dimensional deblurring process to the individual projections and simply combine them to get the unblurred image. This method is known as filtered back projection. This is a projection of an image shown in white and its convolution with the deblurring function shown in yellow. You can see that the deblurring tends to sharpen rapid changes in the projection. This is the effect on the profile of the circular object that was reconstructed by back projection earlier. The regions outside the confines of the object are now negative, where in the unfiltered back projection the image was positive. Also, the region from within the object itself now has a flat profile and does not have the maximum seen in the projection. We can now do the same process of back projection as before, except using the filtered projections. Here is a section through the reconstructed object with the unfiltered reconstruction in red and the filtered reconstruction in white. The filtered back projection has a rectangular profile with a small amount of noise outside it. The improvement in reconstruction quality is clear, and that is the principle of CT. CT scanning has undergone rapid and explosive development. The first major innovation was introduction of fan beam geometry, in which multiple rays could be measured simultaneously. Advances in microprocessor technology allowed multiple processors to back-end the detectors, which allowed rapid assimilation of data, reorganization of rays, and convolutions. These fed into a higher order of processor that performed the back projection and image analysis, so vastly reducing the time in which an image was produced following a scan. Finally, this resulted in a fixed detector array with simply a rotating X-ray source. This arrangement allowed very rapid scanning. The recent thrust has been towards full three-dimensional imaging. This has been achieved by helical scanning with translation of the X-ray table through the scanning beam, so-called helical scanning, or by use of multiple slices in the detection geometry, giving a full three-dimensional image. Here are some results of three-dimensional scanning. While people have become rather blasé about the results of medical imaging, these sort of results are absolutely astounding. When I was a medical student, at a time when CT was just starting, this would have been completely unimaginable. The potential of imaging of this quality to influence medicine has not yet been realized, but it will be absolutely transformational. Finally, I would like to end with this thought. Thank you very much.